Inception and Googlenet. The Inception network came to the world in the year 2014 when a group of researchers at Google published their paper. And the title of the paper is Going Deeper with Convolutions. The main hallmark of this architecture is building a much deeper neural network. At the same time, keep improving the utilization of the computing resources inside the network. And this GoogleNet architecture was used in their submission for ILS-VRC 14. And the GoogleNet, which uses a 22 layers deep network, which is deeper than VGGNet, and it reduces the number of parameters 12 times lesser. If you remember, the VGGNet, which had about 138 million parameters, whereas the GoogleNet has only about 13 million parameters, which is 12 times lesser. And at the same time, the interesting part is it achieves much significantly more accurate results. Now let's look at the novel features of Inception. When you are designing your network, there are some architectural decisions that you need to make for each layer. Decisions like what should the kernel size of the convolution layer be? And we have seen in the earlier architectures, the kernel size varies between 1 by 1, 3 by 3, 5 by 5, and in some cases 11 by 11, like in AlexNet. And the second decision is when to use the pooling layer. For instance, AlexNet uses the pooling layers every 1 or 2 convolution layer to downsize the spatial features. Whereas in the case of VGGNet, which applies pooling after every 2, 3, or 4 convolution layers as the networks get deeper. The configuring these kernel size and positioning the pool layers are the decisions that we need to make mostly by trial and error. But now what the Inception says is instead of choosing a desired filter size in the convolution layer and where to place the pooling layers, let's apply all of them all together in one block. And that's what is called Inception module. And let's have a closer look at how the classical convolutional neural networks, which you can see on the left side, and on the right is the Inception network. From this diagram, we can see the difference. In classical architectures like LeNet, AlexNet, and VGGNet, we stack convolutional and pooling layers on top of each other to build the feature extractors. At the end, we add the dense, fully connected layers to build the classifier. Whereas in the Inception architecture, which is on the right side, we start with the convolution plus pooling layers, then we stack the Inception modules plus pooling layers to build the feature extractors. Then we add the regular dense classifier layers. And now let's unpack this Inception module to understand how it works. A simple representation of the Inception module is shown here. As you can see, the Inception module is a combination of 4 layers. 1 by 1 convolution layer, 3 by 3 convolution layer, 5 by 5 convolution layer, and then 3 by 3 max pooling layer. The outputs of these layers are then concatenated into a single output volume, forming the input of the next stage. The idea is simple to understand. Let's follow this figure. Suppose we have an input dimensional volume from the previous layer of size 32 by 32 by 200. We then feed this input to 4 convolutions simultaneously. The first one is 1 by 1 convolution with a depth of 64 and same padding. The output of this kernel is 32 by 32 by 64. And the second one is 3 by 3 convolution with a depth of 128 and same padding. The output of this kernel is 32 by 32 by 128. Then the third one is 5 by 5 convolution with a depth of 32 and same padding. And here the output of this kernel is 32 by 32 by 32. Now the pooling layer, the 3 by 3 max pooling layer with the same padding and stride is 1 and the output is 32 by 32 by 32. Then we concatenate the depth of the 4 outputs to create one output volume of dimension 32 by 32 by 256. Now we have the inception module, and this takes an input volume of 32 by 32 by 200, and it gives the output volume of 32 by 32 by 256. Now let's look at the inception module with dimensionality reduction. The simple representation of the inception module that we just saw has a big computational cost problem. So this comes with the processing larger filters like 5x5 convolution layer. To get a better sense of that computational problem with this simple representation, now let's calculate the number of operations that will be performed for the 5x5 convolution layer in the example that we shown here. The input volume with the dimensions of 32 by 32 by 200 that will be fed into the 5x5 convolutions of 32 filters with the dimensions 5x5 by 32. This means the total number of multiplications that the computer needs to compute is 32 by 32 by 200 multiplied by 5 by 5 by 32, which all put together, which brings about 163, more than 163 million operations. Now let's look at the dimensionality reduction layer, that is 1x1 convolution layers. The 1x1 convolution layer can reduce the operational cost of 163 million operations to about a 1/10 of that. And that's why this is given the name reduced layer. The idea here is add the 1x1 convolution layer before the bigger kernels like 3x3 and 5x5 convolution to reduce their depth, which in turn will reduce the number of operations. Now let's look at an example here. Suppose we have an input dimension volume of 32 by 32 by 200. We then add a 1x1 convolution with the depth of 16. This will reduce the dimension volume from 200 to 16 channels. We can then apply the 5x5 convolution on the output that has much less depth. If you look at the picture, you can notice that the input of the 32 by 32 by 200 is processed through the 2 convolution layers and outputs a volume of dimensions 32 by 32 by 32, which is the same dimension that we produced before without applying the dimensionality reduction layer. But what we have done here is, instead of processing the 5x5 convolution layer on the entire 200 channels of the input volume, we are taking this huge volume and shrunk its representation to a much smaller intermediate volume, which only has about 16 channels. Now, let's look at the computational cost that is involved in these operations. And also let's compare it to the 163 million multiplications that we got before applying the reduced layer. So the computation is operations in the 1x1 convolution plus the operations in the 5x5 convolution. That is, in the 1x1 convolution, the number of operations are 32 by 32 by 200 multiplied by 1x1 by 16. And this plus the operations in the 5x5 convolution, which is 32 by 32 by 16 multiplied by 5 by 5 by 32. So this comes to 3.2 million plus 13.1 million. Given this, the total number of multiplications in this operation is 16.3 millions, which is 1/10 of the 163 million multiplications that we calculated earlier without the reduced layers. Now let's put the reduced layers in action and build a new inception module with the dimensionality reduction. To do that, we will keep the same concept of concatenating all the 4 layers that we had from the simple representation. Now we will add a 1x1 convolutional reduced layer before the 3x3 and 5x5 convolutions. This will reduce their computational cost. We will also add 1x1 convolution after the 3x3 max pooling layer, because pooling layers don't reduce the depth for their inputs. So we will need to apply the reduced layer to their output before we do the concatenation. And that's what is shown in this picture. Now let's summarize this. If you are building a layer of a neural network and you don't want to have to decide what filter size to use in the convolution layers or when to add pooling layer, the inception module lets you use them all and concatenate the depth of all the outputs. This is called the simple representation of the inception module. Okay, now that we understand the components of the inception module, we are now ready to build the inception network architecture. And here we are going to use the dimension reduction representation of the inception module and simply stack them on top of each other and add a 3x3 pooling layer in between for downsampling, and that's what is shown in this picture. In this figure, we stacked two inception modules with the pooling layer in between. We can stack as many inception modules as we want to build a very deep convolutional network. And here is the full Googlenet model, the Googlenet architecture. As you can see from this picture, Googlenet uses a stack of a total of 9 inception blocks and max pooling layer after every several blocks to reduce the dimensionality. To simplify this implementation, let's break down the Googlenet architecture into 3 parts, A, B, and C. In part A, identical to AlexNet and LeNet architectures, where it contains a series of convolutional and pooling layers. And in part B, which contains 9 inception modules stacked like 2 inception modules plus pooling layer, plus 5 inception modules plus pooling layer, plus 2 inception modules. And then finally the part C, which is the classifier part of the network, where it consists of the fully connected and softmax layers. Now let's implement the Googlenet architecture in Keras. First, we build the inception module function to use it in our architecture. Here, if you look at it, the inception module takes the features from the previous module as an input, and it passes it through 4 routes, then concatenate the depth of the output of all the 4 routes, then pass the concatenated output to the next module. The 4 routes are, the first one is 1x1 convolution, and the second route is 1x1 convolution plus 3x3 convolution. And the third route is 1x1 convolution plus 5x5 convolution. Then the fourth one is the 3x3 pooling layer plus 1x1 convolution. Now let's build the inception module function. The function takes the number of filters of each convolution layer as an argument and returns the concatenated output. The table here summarizes the hyperparameter setup for the Googlenet architecture. And this is the one which is implemented by the authors in the original paper, going deeper with the convolutions. And this is the architecture. That's the Googlenet architecture, is the winner of the ILS VRC 2014 competition. And it achieved a top 5 error rate of 6.67, which was very close to human level performance and much better than the previous convolutional neural networks like AlexNet and VGGNet.